All right. I will begin. Heavenly Father, we thank you for this day. Again, Lord, I thank you for the students, and I just pray you bless this class today, Lord. In your name I pray. Amen. All right, so I should make sure I provide you a definition since, well, I'm going to be talking about it from time to time, so probably be the decent thing to do to actually write it down. So this is definition 9.6.19, and it says the following: let V be an inner product space, and S a linear transformation from V to V. All right. For which the range of S perp is the kernel of S. And this is redundant, but just to emphasize for pedagogical reasons, the perp of the kernel of S is the range of S. All right, then S an orthogonal projection. All right. I mean, in principle, you could have a projection which is not orthogonal. And let me see if I can come up with an example of a projection which is not orthogonal, something like, well, actually, let me not get distracted. An example, so, you know, like, well, what's the idea of this? What could you say about V in this context? So here, V would be the direct sum of the kernel of S. Oh, man, that's just... horrible. So in this context, we'd have V as the direct sum of the kernel of S, right? And the, well, the range of S, actually. Because remember, generically speaking, what's the theorem that we have? Remember we have this theorem? That W direct sum the perp of W is what? It's the whole vector space in the context of an inner product space. So if you think about W being the kernel, of course the direct sum of the kernel and its perp is the whole space. But when the perp of the kernel is the range, you get this. And so let me just write a formula. So basically we've got S of, let's say, you know, x of naught plus x1, and it's just equal to what? It's equal to I said the range, what is the range of S? So here, I'm supposing x naught is in the kernel of S, and, oh, well then it's clear what this is, right? If x naught's in the kernel of S, what happens here? It's not. What does the kernel mean? It gets what? Sent to 0, right? So the formula is what? S of this sum is just equal to x1. So you're removing the piece which is in the direction of the kernel of S. But also x1 is an element of, you know, the perp. Anyway, this is a orthogonal projection. They have special properties. And actually, I'm not super interested in this, so I don't know why I'm spending so much time on it. Let me show you an example. Suppose I let A equal to 3 UU transpose plus 7v v transpose, where suppose beta u comma v is orthonormal basis. For R2. So we could come up with specific vectors for u and v here, but I wanted to do it symbolically so that you can better appreciate what's going on here. Yeah? No? Oh, okay. What does it mean to say that it's orthonormal? First of all, does this make sense? What kind of matrix is this? This is a 2 by 2 matrix, right? Because we're looking at like 2 by 1 times a 1 by 2, right? So it makes sense that this is a 2 by 2 real matrix, yeah? So if your matrix looks like this, you can find eigenvectors for it pretty easily. All right? What's an eigenvector for A? Well, before I get to that, what does orthonormality mean? We have u dot v, which is, by the way, u transpose v, equals to 0. We have u dot u, which is, by the way, u transpose u, and v dot v, which is, by the way, v transpose v. These are all, well, 0, 1, and 1, right? That's what we mean by orthonormal, right? So what happens if you take this A and you multiply it by u? What happens then? What's AU equal to? So this piece, what? This piece dies. And when this hits that, you get 1, right? So you're left with 3u. And if we take A times V, what do we get? This time, this piece, when we hit that times that, we get 0. And then, of course, V transpose V is 1. We're left with 7 times V. So what are the eigenvalues for this matrix? A has eigenvalues lambda 1 equals to 3 and lambda 2 equals to 7. And of course, you have eigenvector u and v with those eigenvalues respectively. So in this context, I can tell you an example of an S, so to speak. Like S, in the sense of the definition I just wrote down. We could say S of x is equal to, for example, u transpose times x. What would that do? What's the kernel of S then? Span of V, right? What's the range of S? It's the lambda equals to 3 eigenspace, yeah? And maybe I should call this S sub 3 or something, you know, to indicate it's the third eigenvalue. I don't know. You could also define, you know, S sub 7, right, by V transpose times X. That would have the kernel. By the way, this was what the lambda equals 7 eigenspace, right? So vice versa, the kernel of S7 is the lambda equals to 3 eigenspace, and the range of S7 is the lambda equals 7 eigenspace. All right, anyway. So you could look at these, right? So what's going on here? S sub 3, it's a mapping from the direct sum of the lambda equals to 3 eigenspace and the lambda equals to 7 eigenspace. And what's it mapping to? It's mapping to just the 3 eigenspace, right? And likewise for S7, it maps to the lambda equals 7 eigenspace. Both S3 and S7 are examples of orthogonal projections. So we can build orthogonal projections from an orthonormal basis. If you give me an orthonormal basis, I can use it to build orthogonal projectors. It's pretty easy. You just multiply the basis times its transpose. It gives you these little rank 1 matrices which project onto the eigenspace like you want. I mean, if you think about what this thing is, just in terms of just raw matrix theory, just think about, this right here. What are you doing? You're looking at some linear combination, some multiple of u basically is what that matrix, what that transform does. So, I mean, it's going to build some multiple of u from the input. Anyway, okay, enough. And so the real spectral theorem basically says the following. If we have A, and I'll just stick with the matrix version of it, okay? But if A is an element of Rn by n, and A transpose equals to A, all right? In other words, it's a symmetric matrix, then there exists an orthonormal eigenbasis, orthonormal eigenbasis, beta, let's say, v1, v2, vn, right? So in other words, you can diagonalize it with respect to the, with respect to an orthonormal eigenbasis, and a little bit more than that. If we say epsilon, well, rather E sub I is the kernel. Oh, excuse me, I'm doing the matrix one. So let's say the null space of curses. Anyway, if we're doing the transformation, we'd have to say self-adjoint, right? That's anyway. In other words, it has a symmetric matrix. So the null space of A minus lambda sub II, right? If you want, I can put a J here to make it easier to see. And here, the jth eigenspace, null space of A minus lambda ij. Then you have the following. A Rn, it's the direct sum of the eigenspaces. However many you got, let's say k, all right? And B, if you calculate, if you say that epsilon hat sub j is the direct sum of I not equal to j of epsilon sub I. So do you understand what I mean here? I mean direct sum of everything except for the jth one, right? Then this has the orthogonal complement to that is, guess what? It's just the jth eigenspace, which is to say that the eigenspaces, they're not just independent, they're complementary in the sense of the geometry. Like if you take one and ask what the perp of one of them is, it's the rest of them. If I was to take a couple of them, for example, if I was to take the first two If I asked you what the perp of epsilon 1 direct sum epsilon E1 plus E2 perp was, guess what it would be? It would be everything else. That's the way this works. I mean, that's not what the theorem says, but that's in fact also true. So this notion of perp is very, very sort of easy to understand. C, there's orthogonal projections, which I'm using T sub I here for. T sub I and T sub j is equal to Kronecker delta ij Ti for 1 less than or equal to I comma j less than or equal to k. Here the T sub I is a mapping from Rn to the ith eigenspace. It's an orthogonal projection onto the ith eigenspace. That ith projector will kill everything except for eigenvalues with eigenvectors with eigenvalue I. That's the Ti and Tj, it's analogous to my S3 and S7 in the example I just did. More than that, you can build the identity map from the sum of these things. And finally, and this is really the beautiful part, the transformation itself is lambda 1 T1. I seem to have transitioned to talking about transformation. My apologies. I'll make the connection explicit here for a second. So in all of these, I'm assuming that T has standard matrix A. All right. The theorem that's in the notes is a little bit more general. It's stated for like a real inner product space, which is not necessarily column vectors, but I'm really interested in column vectors today, so I'm stating it for column vectors, all right? But there's more than, I mean, really, this is great, but it's more than just this. I can actually build, the T sub i's in the same way I did in the example here. All right, like if you wanted me to tell you what's the matrix of Ti like that, it would be something like Vi transpose, provided that lambda I had just one eigenvector. If you have more than one eigenvector, you need like a sum of these or something, but I don't want to get into all that. Another example. If we look at A equal to 2, 2, minus 1, 2, 2, minus 1, minus 1, minus 1, 5, then I can tell you that this has lambda 1 equal to 3. I can tell you it has lambda 2 equal to 0, and I can tell you it has lambda 3 equals to 6. How do I know that? The reason I know that is the way I made up this example was to construct, let me tell you how I made up this example. I constructed beta, an orthonormal basis rather for R3 as follows. My first thing on my basis was 1 over the square root of 3, 1, 1, 1. Then I made something perpendicular to that, 1 over the square root of 2, 1 minus 1, 0. All right? Now I was trying to find an orthonormal basis for R3. How do you think I made my third vector? If this is U1, this is U2. How do you think I constructed, I want a third vector which is perpendicular? In R3, there's something you can do that you should have confidence in doing if you had calculus 3. You want a perpendicular vector for a given pair? Yes, the cross product. I took the cross product of U1 and U2. That gave me my third vector, U3. What's the magnitude of the cross product? It's the product of the magnitudes times the sine of the angle between them, is it not? So when you take a unit vector across a unit vector, you know what you get? You get another unit vector if they're already perpendicular, like these are. So I know, without further calculation, that U3 is normalized. Furthermore, by construction, it's perpendicular to U1 and U2. So that's how I construct a basis for R3 sometimes. I use the cross product. And I start somewhere, and then this second one's always easy to come up with just by like guesstimation, you know? The third one is the tricky one, but the cross product fixes that. So there's my orthonormal basis. What does it have to do with A? Well, the way I made up this A is as follows. I said, well, I'm going to make A equal to 3 U1 transpose plus 6 U3 transpose. Then I know the real spectral theorem, and I understand, well, the example I just showed you, so I know this trick already. You notice then, what's the missing link here? I don't have any U2 term, right? So there's 0 there. That's how I knew as soon as I wrote this down, and this works out to that. All right? As soon as I write this down, I know by construction it's going to have eigenvalue 3 with eigenvector U1. We're going to have eigenvalue 6 with eigenvector U3. And we're going to have eigenvalue 0 for the eigenvector U2 by construction. So this is kind of neat, because we've spent a fair amount of time looking at how to take a given matrix and determine what its eigenvalues are, right? Now I'm giving you a little bit of a window into how you can make matrices with a given eigenvalue. And they don't have to be something stupid, just like, I mean, we always take a diagonal matrix, right? And give it whatever eigenvalues you want, right? You want a 5 by 5 matrix with eigenvalues 1, 2, 3, 4, 5. You should go, okay, done. There you go, diagonal. Eigenvalues 1, 2, 3, 4, 5. Eigenvectors E1, E2, E3, E4, E5. Done, right? But suppose you want a more interesting example. Well, this real spectral theorem gives you a way to make them. All right, anyway, I personally think that's interesting. You can disagree if you want, but yeah.
Actually, you're trying to find a third orthogonal vector using the cross product, but what if you have 3 vectors?
Oh, so glad you asked. So what if you wanted to find a fourth vector in R4, and you already had 3 that were orthonormal? Well, you could look at the lesser known cross product, which has the following mnemonic. Formally, that will produce the vector you want. This is nowhere in the notes. I'm showing you a cheat to get V4. There are 2 other nice ways to find, I know which problem you're talking about. I've talked to several students about this already. To find V4, the problem we're talking about is you're already given a basis where you've got V1, V2, V3, right? And the question is, what do you put here to get an orthonormal basis for R4? These are already orthonormal, right? Those are already orthonormal. So you just got to pick out V4 somehow. We need to come up with a normalized vector that finishes the basis for R4. 2 ways to do this. One way, which is nice, is just to say, okay, so I'm just trying to solve the equation A, B, C, D dot V1 or dot V2 or dot V3 equal to 0, right? Which, if you look at it, is 3 equations and 4 unknowns. All you got to do is find a basis for the null space, bam. That is in the direction that you want for V4. Normalize it, you're done. That's one way you could do it. Just solve the problem directly. Find an orthogonal vector to the given 3 vectors. This is not that hard. I've seen people do it in about 1/3 of a page. The other way is to think more geometrically and think about this being, W being the span of the given orthonormal vectors, right? And if you just pick any x off the plane, well, volume, really, hyperplane, as long as you're not so unlucky as to pick x which is tangent to the plane, you can calculate, the projection onto W of x, right? That's the piece of x which you don't care about, and the, let's say, v4 prime you're interested in is this guy. In other words, I'm saying you can calculate v4 prime by x minus v1 dot, goodness gracious, by x dot v1, v1 minus x dot v2, v2 minus x dot v3, v3 like so. All I'm really telling you is run Gram-Schmidt on the set v1, v2, v3, v4x. But when you run Gram-Schmidt on an already normalized, orthonormalized set of vectors, it's very boring. It does nothing. It just sends back the first three vectors which you started with. I mean, you run Gram-Schmidt on beta. Gram-Schmidt's very boring all the way up until the question mark, because I already gave you an orthonormalized set up to the fourth one that you don't know yet. That's the mystery one. So if you run Gram-Schmidt, the fourth run, you do this. You subtract off this piece right here is the projection onto W of x, and that should give you a vector which is in the same direction as the solution to method number 1. So this is the third way. But, I mean, here's 3 different ways to find that fourth vector. After you're done with that, you still have to normalize v4 to get the actual normal vector. But which one's easier? I don't know. I think they're all about the same noise. Maybe this, actually. I think this is maybe the cleanest, just in terms of, I don't know, Gram-Schmidt for me, once you get past about 2 or 3 things, it starts to get like, the arithmetic gets a little hairy. Yeah? But. Okay, so there's that. But that's you know, that's one of the really nice things. If you look at what we've done, is I mean, there's one very important tool, and you know, I didn't spend a lot of time on this, but it's so important. If we have S is a subset of Rn, right? Then the perp of S, right? And suppose this is a finite set. So I'm thinking, you know, S is equal to something like S1, S2, maybe it's got K vectors in it, right? The perp to this set is the null space of the matrix of S transposed. And null space, that's not a big deal. Like, you can do that calculation. That's what's driving method number 1 here, right? See, because what this really is we're calculating the null space of what? If you actually go through the details, it's v1 transpose, v2 transpose, v3 transpose. But if you're smart, you'll throw away the pesky renormalization constants to have integer algebra to do there. Right? But check it out. I mean, that's nothing more than the null space of, say, gamma transpose, if I think of these first 3 as being gamma. Yeah. So, but Gram-Schmidt's also a useful tool. Yeah. All right, anyway. So let me turn the page here. The next chapter in the story here is on quadratic forms, which is actually more of the same. So I'll tell you what is a quadratic form? I'm sorry, I really probably shouldn't have even written this theorem out again. I think it's a waste of our time a little bit today, and I'm sorry I did that. Oh well. I'm much more interested in what I'm about to do for today. So, what is a quadratic form? Oh. Yeah. So actually, what we're about to cover answers some questions that may have been sort of sitting in the background for you since your high school algebra days. All right? So let me just kind of frame the discussion a little bit here. You know how to do things like, for example, if I give you guys x squared over 9 plus y squared over 4 equals to 1, everybody can tell me that's in a what? The solution set to this is a ellipse. Yes, okay, very good. And if I was to say x squared minus y squared equals to 1, everyone would tell me it is a circle. No. 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 Try again. Hyperbola, yes, okay. Here we go. And if I was to say something like, I don't know, xy equals to 1, you would tell me it's a, or if I was to tell you x squared plus 4xy plus 5y squared equals to 1, you'd tell me it's a, you wouldn't tell me, right? Maybe if you really had a good instructor, you were taught that xy equals to 1 is also hyperbola. Right? I don't know if you've ever thought about this, but this, graphically, y equals 1 over x, right? Y equals 1 over x is, it looks like this, right? That's a hyperbola that's been rotated, right? So how do you understand, I mean, so what I'm trying to tell you is the things we focus our attention on in algebra these days, they're really special, right? Because they're missing this kind of term. Or this kind of term. I call these cross terms. So cross terms cloud the direct reading of the equation, the level surface. Similar comments go for functions of 3 variables, right? If you've had calculus 3, everybody knows x squared plus y squared plus z squared equals to 1 is the unit sphere, right? And also, you know that if you've got x squared minus y squared minus z squared equals to 1, it's like a hyperboloid, right? And if you put x squared plus y squared, but you know what happens if you had plus 2xy plus 2xz, minus z squared equals to 1? Nobody knows what that is now. Because it's got cross terms. It's not clear. You won't find it on the list of standard examples in your Calculus 3 book. And the reason for this is pretty simple. We need linear algebra to unravel the cross terms. And we have all the tools we need to do it. They're just sitting here waiting for us to use. Okay. So all of these basically are quadratic forms set equal to a constant. What's a quadratic form? A quadratic form, I'll say Q, on Rn has formula, I should say. Here's the formula. Q of x is equal to x transpose AX, where we insist that A transpose equals to A. So let me just show you, how do you find the matrix of a quadratic form? This is different than finding the matrix of a linear transformation, right? This is a new kind of matrix in terms of its association. So here's an example. If we had, let's say, Q of x1 comma x2 equal to x1, x1 plus 2 x1 x2 plus 3 x2 x2. That formula is actually an example of a quadratic form. Let me show you how we rewrite that. We rewrite that as x1 comma x2, some 2 by 2 matrix, x1, x2. I'll do the easy part. 1, 3. What about that 2? Yeah, 1 and 1. So the proof is in the pudding, so to speak. I mean, if you multiply that out, you get the formula back again. Another example. This time I'll use x, y, z for my scalar variables. So if I had q of x, y, z equal to, oh, I don't know, how about like 2x squared plus 2y squared plus 5z squared plus 4xy minus 2xz. Just thinking of this random formula. Let's see here, minus 2yz. This would be a quadratic form. You can write it as the row vector x, y, z times a matrix times column vector x, y, z. Of course, not accident, I made it this matrix. That was intentional. So we have a 2, a 5. That's from these terms. The xy term gives me a 2 here and here. The xz term gives me a minus 1 here and here. And finally, the minus 2yz term gives me the remaining minus 1s in the matrix. So finding the matrix of a quadratic form is not a big deal, right? It's almost embarrassing to put as a test question, right? How do you guys feel about finding the matrix of a quadratic form as a test question? I see some yes, please. Lots of those. Yes, okay. Good, very good. So guys, what we talk about, I mean, I keep saying these words, orthonormally diagonalizable. Well, that's a lot to say, isn't it? What does that mean? What does it mean for beta, v1, v2, vn, orthonormal basis for Rn? What's that tell us? That tells us that, you know, v sub I dot v sub j is equal to 0, right? Which tells me that vi transpose vj is equal to, not 0, come on, not 0, Kronecker delta ij, right? Kronecker delta ij. And if you look at what this means, translate it into a statement about the basis matrix, this says that the basis matrix transpose times the basis matrix is equal to the identity matrix. To which we say, yay, because this says that the inverse of the basis matrix for an orthonormal basis is just the transpose. And so what you know, if we suppose we have x is equal to, let's say, y1 v1 plus y2 v2 plus plus yn vn, right? In other words, the coordinate vector of x with respect to the beta basis is the y1s through yn's, right? What was our formula for finding the coordinates with respect to a non-standard basis in Rn? Remember what we do? We take the vector and we multiply it by the inverse to the basis matrix, right? So generically speaking, this was beta inverse times x. But here, it's straight up beta transpose times x. Right? So let's just, look at a generic quadratic form here for a bit. And then I'll get back to my examples. Won't be long. I'll say something about these examples, which is quite beautiful. So let's see here. We start with a formula. Let's say we have a quadratic form, q of x equals to x transpose ax. Right here, a is equal to a transpose. So what's that mean? Real spectral theorem applies. That means we can find an orthonormal eigenbasis for A. So let's change this formula. Let's make this formula in terms of y instead of x. So, let y equal to the transpose times x, where, again, beta, I'm assuming, is an orthonormal basis. But actually, I'm assuming here where beta v1 through vn, orthonormal, and a times vj is equal to lambda j vj. That is to say, assume you have an orthonormal eigenbasis for A. The real spectral theorem says I can find it, and I know that all the lambdas are real. Woohoo! So now you just got to use your imagination a little bit. How do I rewrite this formula for x as a formula for y? How do I trade my x's for y's? May I recommend solving this? This tells me that x is equal to what? It's equal to beta y. Right? And what about x transpose? Looks like a y transpose, beta transpose, yeah? Sock shoes? Okay, so take these, plug them in up here. What happens? We got ourselves a y transpose, beta transpose, a beta y. Which is, by the way, what? Y transpose beta inverse, because it's orthonormal basis, remember, a beta y. But what have we done? What does it mean to take the matrix and put P inverse AP, where P is filled with eigenvectors? It diagonalizes it, right? So what you're looking at here is y transpose, lambda 1, lambda 2, lambda n, y. And if you want a formula, that's lambda 1, y1 squared, lambda 2, y2 squared, plus lambda n, yn squared. In other words, if you can find the eigenvalues for a quadratic form, you can classify what kind of quadratic form you're looking at. If you think about it, if both of the eigenvalues, if we were looking at a two-dimensional case, if both of the eigenvalues are positive, if we set that quadratic form equal to a constant, a positive constant, it's going to be like an ellipse. If one of the eigenvalues is positive and one of them is negative, you set that quadratic form equal to a constant, it's going to be like a hyperbola. If one of them's 0 and the other one's not, it's going to be like a parabola. Or paralines, actually, I should say. But anyway. So over here, I can tell you that if we were to work out the formula for this, we could rewrite this formula in terms of eigenvalue 3 and eigenvalue 6. It would be 3 times, let's say, x bar squared plus 6 times z bar squared, where xyz is explicitly equal to x bar u1 plus y bar u2 plus z bar u3. For the u1, u2, and u3, I told you how to construct, forming the orthonormal eigenbasis for this matrix. And so, see, when I set this formula, right? When I set that formula, this horrible formula, q of xyz, right, equal to 1. What is it? I mean, on the one hand, it's 1 is equal to 2x squared plus 2y squared plus 5z squared plus 4xy minus 2xz minus 2yz. Oh, what is that? Well, that in eigencoordinates is 1 is equal to 3x bar squared plus 6z bar squared. And you see you can draw a picture, something. Maybe this is your x bar, this is your y bar, this is your z bar. What is that? If you've studied if you haven't studied calculus 3 and you don't know what that is, no shame. If you studied calculus 3 and you can't tell me what 1 equals to 3x squared plus 6z squared is a small but non-negligible amount of shame. But it spreads around, so it's not that big. Because it seems like it's a common shame. What is it? What is it? I heard it. It's a cylinder, right. Yeah, this is nothing more than a cylinder along the y-axis, right? So it's something like the y-bar axis, rather. It's kind of some kind of cylinder. This is if I set that equal to 1, we're looking at a cylinder with axis. What's the axis of the cylinder? U2. U2 points along the axis of the cylinder. U1 and U3 are the semi-major and semi-minor axes of the cylinder. These things are all revealed to us by the real spectral theorem. So maybe you can start to understand why I'm excited about this theorem, because it allows me to see past things that I just could not see before I knew linear algebra. And while I have not shown you today, in the notes, I go through the explicit procedure to actually to find the coordinate change formulas, to change from like xy to x bar, y bar, to like remove the cross terms. I mean, I think I've shown you everything you need to do that. But anyway, so that's it for today. Thanks, guys. Oh, sorry I didn't take attendance. Don't tell anyone.